Our solar system feels normal, a steady star. A few rocky worlds close in, giant planets farther out. One small planet, quietly circling in just the right place. For a long time, that felt like the default. If stars form planets everywhere, then systems like ours should be common, familiar, repeatable. But then we started looking more carefully. As astronomers discovered thousands of planets around other stars, a strange pattern emerged. We didn't find copies of home. Instead, we found crowded systems, with large planets pressed tightly against their stars. We found super-Earths, worlds bigger than anything in our system, appearing again and again. And yet, here, there are none. No super-Earths. A massive planet like Jupiter sitting far away, quietly stable. Orbits that have remained calm for billions of years. The more we learned about other planetary systems, the more unusual our own began to look. Not because of Earth alone, but because of everything around it. So tonight, we're not asking whether Earth is special. We're asking something much bigger. What if the entire solar system is rare? And what if only now, with new tools and new ways of seeing, we're finally close to finding out? Fan 2. Planets are common, but places like our home, they seem incredibly rare. This contrast is the greatest mystery scientists are currently fighting to solve. Over the past few decades, we have discovered thousands of worlds out there. Many stars host a crowded house, packed systems where planets huddle close to their sun, racing at breakneck speeds, completing an entire orbit in just a few days. At first, everyone assumed the universe would be overflowing with systems just like our own. But the reality turned out to be the exact opposite. The more we look, the more weird places we find. Gas giants squeezed tight against their stars, and planets constantly colliding or shoving each other out of position. Nowhere do we see a layout like ours. Small, rocky worlds on the inside, and distant giants guarding the outskirts. Why is that? Are we truly a one-of-a-kind cosmic fluke? The answer might lie in the way we look at the world. Imagine you are at a loud, crowded party. You easily notice the people shouting or dancing right in front of you. But the people sitting quietly in the corner of the room, you might never even know they're there. Exoplanets are the same way. Our current tools are mostly tuned to find the noisy ones, the massive planets that move fast and stay close to their stars. Our solar system, however, is the quiet type. Take Jupiter, for example. It sits far away and moves slowly, taking nearly 12 years to complete a single trip around the Sun. Seen from a distant star, Jupiter's influence would be like a faint whisper, easily missed unless you have the patience to listen for decades. And here is the most important part. That very quietness and distance are what protect us. Life needs time. It needs billions of years of peace, free from collisions or chaotic orbital shifts, to evolve. A system where planets are constantly shoving and crowding each other is a very difficult place for life to survive long-term. So, when we ask, is the solar system rare? What we are really asking is peace and stability rare in this universe? Perhaps we aren't alone. Perhaps we've just been trying to find quiet friends using tools that can only hear the noise. To understand why our solar system feels so unusual, we need to step back and look at something astronomers call planetary architecture. Planetary architecture isn't about how many planets a system has, or whether one of them might be habitable. It's about structure. It's about where planets sit, how they're spaced, and how their sizes change as you move outward from the star. When astronomers talk about architecture, they're asking a simple question. Does the system look organized, or does it look chaotic? Our solar system answers that question very clearly. Closest to the Sun, we find small, rocky worlds: Mercury, Venus, Earth, and Mars. Dense planets made mostly of metal and stone. Farther out, beyond a wide, empty gap, we encounter something completely different: massive gas giants, Jupiter and Saturn. Worlds hundreds of times more massive than Earth, composed largely of hydrogen and helium. And beyond them, even smaller icy bodies, drifting quietly at the edge of the system. This arrangement isn't random. It looks layered, almost deliberate. Small planets inside, the big planets outside. Clear spacing between major regions. It's the kind of structure you might expect if everything formed calmly, each component settling into its place without constant disruption. In fact, from the inside, it feels so intuitive that we rarely question it. Of course, the rocky planets are close in. Of course, the gas giants are farther out. But nature doesn't usually work that way. When astronomers began discovering other planetary systems, they expected to see similar layouts repeating across the galaxy. Instead, they found something very different. Planets of wildly different sizes sharing tight orbits. Massive worlds sitting where small ones should be. Entire systems compressed into regions smaller than the orbit of Mercury. In that broader context, the solar system starts to stand out. Its planets don't crowd each other. Their orbits don't overlap or constantly tug at one another. Each world occupies a distinct zone, as if the system had time, millions of years, to sort itself out. This kind of structure has a name. Astronomers call it an ordered system. An ordered system is one where planets are arranged by size and composition in a predictable way, where the inner regions are dominated by rocky worlds and the outer regions by gas and ice, where long-term stability seems built into the layout itself. And that's where the mystery deepens, because order like this isn't what we expect by default. Planet formation is messy. Young systems are violent places, filled with collisions, migrations, and gravitational chaos. Left unchecked, that chaos usually leaves behind crowded, irregular systems, not neat, layered ones. So when we see this level of organization, we have to ask why. Why did the solar system end up this way when so many others did not? Why did its planets sort themselves so cleanly instead of collapsing into disorder? For now, we won't answer those questions. But we can say this much with confidence. The kind of order we see here is not the norm. And when astronomers began to count just how often this kind of order appears elsewhere in the galaxy, the results were surprising enough to change the conversation entirely. And when astronomers started counting how often this kind of order appears, the numbers were startling. Once astronomers began comparing planetary systems side by side, the sense that something was unusual about our own system could finally be tested with numbers. And the numbers were striking. When researchers looked not just at individual planets, but at the overall layout of entire systems, they found that fewer than 1% showed the kind of ordered structure we see in the solar system. Less than 1% had small, rocky planets neatly arranged on the inside, with large gas giants confined to distant, stable orbits farther out. At first glance, that figure seems almost too small to be meaningful. But it holds up across different surveys, different methods, and different samples. No matter how astronomers sliced the data, the results stayed the same. Systems with this level of organization were rare. What's important here is why they're rare. It isn't because most systems have fewer planets. Many have more. It isn't because our system happens to have 8 worlds instead of 5 or 6. And it isn't because one planet, Earth, ended up in the right place. The defining feature isn't the number of planets. It's the arrangement. Most planetary systems don't separate cleanly into regions. They mix sizes. Large planets appear close in. Smaller ones are scattered among them. Orbits are packed tightly together, leaving little room for long-term calm. These systems may be stable for a while, but their structure reflects a history of strong interactions and frequent rearrangement. The solar system tells a different story. Here, the planets are spaced widely enough to avoid constant gravitational interference. Their sizes change gradually as you move outward. Each region feels settled, as if the system reached a quiet equilibrium early on and stayed there. That combination, wide spacing, clear separation, and long-term stability, is what makes this architecture unusual. And when astronomers look for it elsewhere, they almost never find it. This is the moment when the question shifts. It's no longer enough to say the solar system is different. It's more accurate to say it's an outlier, and that distinction matters. Because outliers usually demand an explanation. Random chance alone struggles to produce this level of order. In a process as chaotic as planet formation, tidy outcomes are not the default. Collisions, migrations, and gravitational tug-of-war tend to blur boundaries, not sharpen them. They create crowded systems, not layered ones. So, if fewer than 1% of systems look like ours, then something specific must have happened here. Something that prevented large planets from drifting inward. Something that cleared material at just the right time. Something that allowed the system to settle before chaos could take over. That realization closes the door on the simplest explanations. The solar system isn't ordered by accident, and it isn't ordered just because it formed later or more slowly. Its structure points to a particular history, one shaped by movement, timing, and events that unfolded early, when everything was still forming. If we want to understand why this kind of order is so rare, we can't stay in the present. We have to look backward, far backward, to a time when the solar system was anything but calm. To understand why this kind of order is so rare, we have to rewind the clock back to the violent early days of our solar system. When astronomers first began analyzing large numbers of planetary systems, a very different picture of the universe came into focus. According to data from the Kepler mission, systems with many planets are not unusual at all. In fact, they're common. Many stars host not just 1 or 2 worlds, but entire clusters of planets orbiting together in tight formation. From the universe's perspective, complexity seems to be the norm. But this complexity rarely looks like what we see at home. One of the most common patterns astronomers discovered is often described as peas in a pod. In these systems, planets tend to have similar sizes and masses. They form a compact group orbiting close to their star, with each planet only slightly farther out than the one before it. The spacing between them is small, and the entire system fits into a surprisingly tiny region of space. Some of the best-known examples make this contrast clear. Kepler 90, for instance, has 8 known planets, just like our solar system. But while our planets are spread across billions of kilometers, all 8 of Kepler 90's worlds orbit closer to their star than Earth does to the Sun. TRAPPIST-1 takes this compression even further. It hosts 7 Earth-sized planets, all packed into a region smaller than Mercury's orbit. Their years last just days. Their gravitational interactions are strong and constant. It's a system that feels busy, energetic, and tightly wound. And systems like these are not rare exceptions. They appear again and again in the data. It's important to pause here and be clear about something. These systems aren't mistakes. They're not broken. They're simply the most common outcome of planet formation that we've been able to observe so far. From the universe's point of view, this is what normal looks like. So why do we see so many of them? Part of the answer lies in how Kepler was designed. The transit method works best when planets orbit close to their star. Short orbits mean frequent transits, stronger signals, and quicker confirmations. A system filled with tightly packed planets announces itself loudly and repeatedly. A calm, spread-out system does not. So Kepler revealed a universe full of compact architectures, systems where planets crowd together, interact strongly, and evolve in close quarters. This became the new baseline, the pattern astronomers came to expect when they looked elsewhere in the galaxy. And against that backdrop, the solar system begins to feel strangely empty. Our planets aren't packed together. They don't share tight orbital lanes. Vast regions of space separate one world from the next. Compared to the crowded systems Kepler uncovered, our system looks quiet, sparse, almost unfinished. That contrast is the key. If crowded, compact systems are the universe's default, then the solar system isn't just different, it's missing something. And once you notice that absence, a deeper mystery begins to take shape. And when we look closer at what these crowded systems contain, another mystery begins to emerge. Once astronomers became familiar with crowded planetary systems, another pattern stood out, one that was harder to explain. Across the galaxy, two types of planets appear again and again. They're larger than Earth, but smaller than Neptune. Too big to be rocky worlds like ours, yet too dense to be true gas giants. Astronomers call them super-Earths and mini-Neptunes, and they are everywhere. In surveys of nearby stars, roughly half of all known planetary systems contain at least one of these worlds. Many contain several. They often sit close to their star, forming the backbone of compact systems like the ones Kepler revealed in such abundance. By cosmic standards, these planets are not rare at all. They may, in fact, be the most common kind of planet in the galaxy, which makes their absence here impossible to ignore. Our solar system has no super-Earths, no mini-Neptunes, nothing that fits neatly between the size of Earth and the size of Neptune. This isn't a small omission. It isn't a detail you can explain away by chance. If these planets form easily, and the data suggests they do, then the solar system should have produced at least one, possibly several. But it didn't. For a long time, this gap puzzled astronomers. Why would a system capable of forming gas giants and rocky worlds fail to produce the very planets that appear most often elsewhere? Why does our planetary lineup jump so abruptly from small, dense worlds to distant giants, skipping the middle entirely? The more scientists examined this question, the clearer it became that something fundamental had happened early on. Planet formation begins with dust and gas swirling around a young star. In many systems, that material accumulates quickly in the inner regions, building super-Earths and mini-Neptunes before anything can interfere. Once they form, they tend to stay put, dominating the architecture of the system. But the solar system tells a different story. Here, the inner regions appear to have been cleared out before those planets could fully take shape. The raw material that might have built super-Earths was disrupted, scattered, or removed altogether. Whatever happened, it happened early, and it reshaped the entire system. This is why absence becomes such powerful evidence. What's missing from the solar system isn't random. It's specific. And that specificity points toward a cause. Not a failure of planet formation, but an interruption. A massive influence that altered the course of events before the most common planets in the galaxy ever had a chance to appear. When astronomers follow that line of reasoning far enough, it leads them away from the inner worlds entirely. The explanation doesn't lie with Earth or with the small rocky planets at all. It lies much farther out, somewhere beyond the quiet inner system. A much larger presence must have shaped the outcome, one powerful enough to prevent these planets from forming, and precise enough to leave everything else intact. And once you start looking in that direction, a familiar giant begins to dominate the picture. To understand why the solar system is missing the most common planets in the galaxy, we have to return to the beginning, when nothing here was calm and nothing was fixed in place. In the earliest days, the sun was surrounded by a thick, swirling disk of gas and dust. This was the raw material of planet formation. Tiny grains collided, stuck together, and grew into larger bodies. Over time, those bodies became planetesimals, then protoplanets, worlds still under construction, sharing space with vast clouds of leftover material. It was a crowded, violent environment. Objects collided constantly, orbits shifted, gravity pulled, pushed, and scattered matter in every direction. And in that chaos, one planet began to form faster than the rest. Jupiter. Jupiter didn't start as the giant we know today. But once its core reached a critical size, it began pulling in gas at an extraordinary rate. In a relatively short time, astronomically speaking, it became massive. So massive that it stopped behaving like an ordinary planet in progress and started behaving like an architect. A planet with Jupiter's gravity doesn't simply exist in a system. It shapes the system. It changes what can form, where it can form, and whether it can survive. And here's the part that still surprises people the first time they hear it. Jupiter likely did not form where it is today. In many young planetary systems, large planets don't stay put. They interact with a disk of gas around them. The disk isn't empty space. It's a thick, flowing medium, and it exerts forces that can slowly change a planet's orbit. This process is called planetary migration, and it means that worlds can drift inward or outward over time, like boats carried by a slow current. For a planet as massive as Jupiter, that current can be powerful. In the Grand Tack model, one of the leading explanations for the solar system's unusual architecture, Jupiter formed in the outer system and then began to migrate inward. Not all the way to the sun, but far enough to change everything. As Jupiter moved, it didn't glide through empty space. It plowed through a region filled with building blocks, material that might otherwise have collected into large inner planets. Its gravity disturbed the orbits of countless objects, scattering them, ejecting some, and sending others spiraling inward. In a sense, Jupiter acted like a cosmic broom. It cleared, disrupted, and rearranged the inner disk before it could finish building its largest worlds. And that is where our missing planets may have gone, before they were ever fully born. In many other systems, super-Earths and mini-Neptunes form quickly in the inner regions. They gather mass, grow large, and often become dominant. Once they exist, they tend to shape everything that follows. Their presence is so common that astronomers now treat it as the default outcome of planet formation. But in our solar system, that outcome never happened. If Jupiter swept inward early enough, then the inner region may have been robbed of the time and material needed to build those mid-sized worlds. The ingredients were there, at least for a while. But the construction process was interrupted by a planet that was becoming too powerful too soon. This helps explain something that otherwise looks like an accident. The solar system isn't missing super-Earths because it failed to make planets. It's missing them because the early system was reshaped before those planets could lock themselves into place. And that reshaping wasn't gentle. It was dynamic, violent, full of near misses and unstable paths. A young Jupiter moving inward would have been one of the most disruptive events in the solar system's history. An event that could have determined the fate of every inner world long before Earth even existed. But the story doesn't end with Jupiter moving inward. Because if Jupiter had continued its inward migration, if nothing had stopped it, then the inner solar system might have been wiped clean. The rocky planets might never have formed at all. Earth, in that case, would not be a rare planet. It would be a planet that never had a chance. But if Jupiter had kept moving inward, our story would have ended very differently. Jupiter's inward journey was only half of the story. If it had continued unchecked, the inner solar system would have been stripped of material entirely. The rocky planets might never have formed. What we know as Earth could have been erased before it began, but that didn't happen. And the reason lies with another giant that arrived just in time. Saturn formed later than Jupiter, farther out in the disk of gas and dust. It grew more slowly, taking longer to reach the mass needed to influence the system. But as Saturn gained weight, it began to migrate as well, drifting inward through the same gaseous environment. Eventually, Saturn started to catch up. As the two giants moved closer together, their gravitational interactions became impossible to ignore. Jupiter and Saturn began to lock into a rhythmic relationship known as orbital resonance. Their repeated gravitational tugs started to change the direction of their migration. This was the turning point. Instead of continuing inward, Jupiter slowed. Then, remarkably, it reversed course. Pulled by Saturn's influence and shaped by their shared interaction with the disk, both planets began moving outward together, away from the Sun. This sudden change in direction is what gives the Grand Tack model its name. Like a sailboat changing course, Jupiter tacked inward, then outward, reshaping the solar system in the process. The timing of this reversal was everything. By the time Jupiter turned around, the inner region had been disturbed, but not destroyed. Much of the original material was gone, scattered or pushed outward, but not all of it. Just enough remained to allow smaller rocky planets to finish forming. Mercury, Venus, Earth, and Mars emerged from what was left. They formed from a disk that had been thinned and reshaped, limiting their size and spacing them farther apart than planets in many other systems. This helps explain why Mars is so small, why the inner planets are relatively modest in mass, and why no super-Earths ever appeared. Too early a turn, and Jupiter wouldn't have cleared enough material. Super-Earths might still have formed. Too late, and the inner system would have been wiped clean entirely. There was only a narrow window where this outcome was possible. That's what makes the Grand Tack so compelling and so unsettling. It suggests that the solar system's final structure depended on a precise sequence of events unfolding at just the right pace. A massive planet forming early, another forming later. Two giants meeting at the right distance, at the right time, while enough gas remained to guide their motion. Shift that timing slightly, and the result changes completely. In many systems, giant planets migrate inward and never turn back. They become hot Jupiters, orbiting close to their star and dominating everything around them. In others, large planets form too late to shape the inner regions at all, leaving super-Earths to take over instead. Our system threaded a narrow path between those outcomes, and from that narrow path came something rare. A calm inner system, free of dominant mid-sized planets, with room for small rocky worlds to evolve over billions of years. This is where the sense of relief sets in. What looked like chaos in the early solar system, violent migrations, gravitational upheaval, near destruction, ended up producing long-term order. The same events that threatened to erase the inner planets also set the stage for their survival. Timing was everything. Once Jupiter and Saturn settled into their final orbits, the worst of the turmoil was over. The gas disk faded away. Migration slowed and stopped. The architecture of the solar system became fixed, not because it was perfectly designed, but because it had finally run out of ways to change. From that point forward, the system began to calm. And once the giant planets settled into place, the rest of the solar system finally had a chance to become calm. By now, it's clear that the solar system's story isn't defined by planets alone. The deeper we look, the more we realize that its unusual nature begins even earlier, before any planet ever formed. It begins with a star at the center. Our Sun belongs to a category astronomers call a G-type yellow dwarf. It's a fairly ordinary-looking star by everyday standards. It doesn't flare violently. It doesn't shine with extreme brightness. It doesn't collapse or burn out quickly. From the inside, it feels stable, almost unremarkable. But in the broader context of the galaxy, that kind of star is not the norm. Only about 10% of stars in the Milky Way fall into the same general class as the Sun. Most stars are smaller and cooler. The vast majority, nearly 70%, are red dwarfs. These stars dominate the galaxy by sheer numbers, and many of them host planets of their own. At first glance, that might seem encouraging. More stars should mean more chances for planetary systems like ours. But red dwarfs behave very differently from the Sun, especially early in their lives. Young red dwarfs tend to be active. They flare frequently, releasing intense bursts of radiation. Planets that orbit close enough to receive warmth often become tidally locked, showing one face permanently to their star. Over time, this combination of radiation and tidal forces can strip atmospheres, destabilize climates, and create environments that are far less forgiving than they first appear. The Sun followed a gentler path. It settled into a long, steady phase of nuclear fusion relatively early, maintaining a stable output of energy over billions of years. That consistency matters. It allows planetary climates to evolve gradually instead of being repeatedly reset. It gives atmospheres time to form, oceans time to stabilize, and chemistry time to grow more complex. There's another, less obvious factor that also plays a role: composition. Astronomers use the word metallicity to describe how rich a star is in elements heavier than hydrogen and helium. Despite the name, this includes familiar materials like oxygen, silicon, iron, and carbon, the building blocks of rocky planets. The Sun formed from a cloud that was relatively rich in these heavy elements. Not unusually so, but enough to matter. That chemical richness made it easier for solid planets to assemble in the inner system, giving Earth and its neighbors the raw materials they needed to form dense, terrestrial worlds. Many stars lack that advantage. Some form too early, before the galaxy has been enriched by generations of stellar explosions. Others form in regions where heavy elements are scarce. Their planetary systems, if they form at all, often look very different from ours. Taken together, these factors begin to narrow the path. A star needs to be stable, but not short-lived, calm, but not inactive, rich enough in heavy elements to build solid worlds, but not so massive that it burns out quickly. The Sun fits that profile, but just barely. This is the first quiet constraint in the solar system story. Before we talk about orbits, migrations, or missing planets, we have to acknowledge that not every star offers the same starting conditions. Many stars host planets, but fewer provide an environment where a system can remain calm and predictable for billions of years. In that sense, the Sun isn't extraordinary, but it is uncommon. And once you recognize that, another realization follows naturally. If the star itself is already a narrow match, then everything that forms around it, every planet, every orbit, every long-term interaction, has fewer chances to turn out the same way twice. Yet even a stable, well-behaved star isn't enough on its own, because the next piece of the puzzle, the one that shapes Earth's long-term balance more directly than almost anything else, came from an event that was far less predictable. Even with a stable star, long-term balance is never guaranteed. For Earth, that balance came from something far less orderly, an accident. Among the rocky planets of the solar system, Earth stands apart for one simple reason. It has a moon that is unusually large compared to the size of the planet it orbits. No other terrestrial world in our system has anything close to it. This alone tells us that something rare happened here. The leading explanation is known as the giant impact hypothesis. Early in the solar system's history, when planets were still forming, Earth was struck by a massive object roughly the size of Mars. The collision was violent, but not catastrophic. It didn't shatter the planet. It didn't send Earth spiraling into the Sun. Instead, the impact occurred at just the right angle, at just the right speed. Material was blasted into orbit. Over time, that debris gathered and became the Moon. This was not a gentle event. It was one of the most energetic moments in Earth's history. And yet, its long-term effect was the opposite of chaos. The Moon became a stabilizer. Earth's axis, the invisible line around which the planet spins, is tilted. That tilt is what gives us seasons. But without something to anchor it, that tilt can change dramatically over time. A planet can wobble, sometimes wildly, causing extreme and unpredictable shifts in climate. Mars offers a cautionary example. With no large moon to steady it, Mars's axis has swung back and forth over billions of years. At times, it tilted so far that ice migrated from the poles toward the equator, then back again. Its climate never settled into a long-lasting pattern. Earth's story is different. The Moon acts like a gravitational anchor, keeping Earth's tilt within a relatively narrow range. This doesn't eliminate climate change, but it prevents the most extreme variations. It creates long periods of relative consistency, allowing oceans, atmospheres, and ecosystems to evolve gradually rather than reset repeatedly. Without the Moon, Earth might still exist, but it would likely be a very different world. Its seasons could swing from extreme to extreme. Ice ages might arrive suddenly and end just as abruptly. Entire regions could alternate between frozen and scorched on geological timescales too short for complex life to adapt. And this is where the story becomes quietly unsettling. The giant impact wasn't inevitable. It wasn't guaranteed by physics alone. It required the presence of another large body, moving along just the right trajectory at just the right moment. Too slow, and the impact would have merged the two worlds. Too fast, and Earth could have been torn apart. Too direct, and the result would have been destruction, not a moon. What happened instead was a narrow success. A collision that could have ended Earth's story before it began ended up shaping everything that followed. It transformed a chaotic early planet into one capable of maintaining balance over billions of years. This is what turns randomness into something else. Not design, not destiny, but a rare alignment of events where destruction became foundation. The moon didn't make Earth habitable on its own, but it made Earth predictable enough for habitability to persist. It took a violent moment and turned it into long-term calm. And once that stability took hold, once the Earth-Moon system settled into its quiet rhythm, the effects didn't stop there. Because the same balance that steadied Earth would soon influence the rest of the solar system in ways that were just as important and just as rare. Even though the solar system appears calm today, it still carries clear marks of its violent beginnings. Not all of those marks are planets. Between Mars and Jupiter lies the asteroid belt, a wide region filled with countless rocky fragments. For a long time, it was described as a failed planet, a world that never quite came together. But that idea no longer holds. The asteroid belt isn't the remains of a single shattered planet. It's a region that never had the chance to become one. Jupiter's gravity repeatedly disturbed this zone during the solar system's early history, stirring up material, increasing collision speeds, and preventing those fragments from assembling into a larger body. In other words, the asteroid belt exists not because formation failed, but because interference succeeded. What remains today is a collection of ancient debris, pieces of rock that never melted into a full planet, material that has changed very little since the earliest days of the solar system. In that sense, the asteroid belt is less like rubble and more like a record, a fossil field. Far beyond Neptune, another relic quietly circles the sun. The Kuiper Belt is a vast, cold region filled with icy bodies and small remnants from the solar system's outer edge. These objects move slowly, far from the sun's warmth, largely untouched by the chaos that reshaped the inner regions. Like the asteroid belt, the Kuiper Belt preserves material from the past. But instead of being disturbed by Jupiter, it was protected by distance. Its objects formed early and then remained frozen in place, storing clues about the original structure of the protoplanetary disk. Together, these regions tell a consistent story. The solar system did not emerge fully formed and orderly. It was shaped by motion, disruption, and loss. Material was scattered inward and outward. Some regions were cleared. Others were left behind, isolated and unchanged. And yet, despite all that violence, these structures have remained stable for billions of years. That stability is important. It tells us that the chaos ended, that the major migrations stopped, that the system reached a configuration where large-scale rearrangements no longer occurred. The asteroid belt didn't collapse into a planet. The Kuiper Belt didn't disperse into nothingness. They stayed where they were, quiet witnesses to an earlier era. In this way, the solar system remembers its past. Its imperfections are not flaws. They are evidence, proof that something dramatic once happened and that the system survived it. The scattered debris, the empty gaps, the leftover fragments, all of them point back to a time when order was far from guaranteed. And when you place these fossils alongside the planets, the migrations, and the timing of early events, a larger picture begins to form. The chaos wasn't wasted. It wasn't erased. It was absorbed, settled, and transformed into long-term stability. But the greatest gift of all was something far less visible. When we look at the solar system today, it's easy to forget how turbulent its beginnings were. The planets move along familiar paths. The sun rises and sets with quiet predictability. From the inside, everything feels steady. But that steadiness is not accidental. In astronomy, stability has a very specific meaning. A stable orbit is one that remains nearly circular, with only small variations over long periods of time. It doesn't stretch into extreme shapes. It doesn't cross the paths of neighboring planets. And most importantly, it doesn't drift unpredictably. In our solar system, this kind of stability is the rule, not the exception. The planets follow well-spaced orbits, each occupying its own lane. Their paths are calm enough that, over billions of years, they have avoided close encounters that could trigger cascading chaos. This alone sets the solar system apart from many others we've observed, where planets interact strongly and continue to reshape their systems long after formation. A key reason for this calm lies with the giant planets. Jupiter and Saturn don't just orbit the Sun. They act as gravitational organizers. Their combined mass dominates the outer system, shaping the motion of smaller objects and helping to define the long-term architecture of the entire system. One of their most important roles is often described as a gravitational shield. Countless asteroids and comets drift through the outer regions of planetary systems. In many systems, these objects can move freely toward the inner worlds, increasing the likelihood of catastrophic impacts. In ours, Jupiter and Saturn intercept many of these bodies, deflecting them, capturing them, or flinging them into distant orbits. This doesn't eliminate impacts entirely, but it reduces their frequency. Early in the solar system's history, collisions were common. They shaped planets, carved craters, and delivered materials like water and organic compounds. But over time, those collisions became less frequent and less destructive. The inner planets were given long stretches of relative calm, windows of stability that grew longer as the system aged. And that timing matters. The solar system has maintained this general stability for roughly 4.5 billion years. That's an extraordinary span of time in a universe defined by change. Over that period, the sun has gradually brightened, the planets have cooled and differentiated, and life, at least on one world, has had time to emerge, adapt, and grow more complex. Many planetary systems don't get that chance. In some systems, giant planets migrate late, long after smaller worlds have formed. When that happens, previously stable orbits can be disrupted. Planets can be ejected, collide, or spiral into their star. Even systems that appear calm at first can become unstable hundreds of millions or even billions of years later. In others, crowded architectures remain dynamically active. Planets continue to tug at one another, slowly amplifying small instabilities. Over time, those instabilities grow, turning minor variations into major rearrangements. From the perspective of long-term habitability, these systems live dangerously. Life, as far as we understand it, doesn't require perfect conditions. It can adapt to change. It can survive fluctuations. But it struggles when the ground rules keep shifting. Frequent orbital disruptions, extreme climate swings, or repeated mass extinction level impacts can reset progress faster than complexity can rebuild. This is why stability may be rarer than planets themselves. The universe is good at making worlds. It's good at assembling material into spheres of rock and gas, but creating a system that remains calm long enough for complexity to accumulate, that appears to be much harder. The solar system managed it by threading a narrow path. Its giant planets migrated early, then stopped. Its inner planets formed after the worst disruptions had passed. Its debris was gradually cleared or confined to stable regions. Once the major pieces settled into place, the system entered a long, quiet adulthood. This is the phase we're living in now. Nothing dramatic happens on human timescales. Orbits change slowly. Impacts are rare. The sun shines with dependable consistency. From the outside, this might look unremarkable. From the inside, it feels safe. And that safety is precisely the point. The greatest achievement of the solar system may not be any single planet or event, but the fact that, for billions of years, nothing catastrophic has happened often enough to undo what came before. This kind of calm is easy to overlook. It doesn't announce itself. It doesn't glow or flare. It doesn't show up clearly in early exoplanet surveys. Yet it may be the most valuable ingredient of all. Life doesn't need perfection. It needs time. Time to experiment. Time to adapt. Time to survive mistakes without being erased entirely. The solar system provided that time. By learning, through chaos, to remain calm, it became a place where complexity could slowly take hold, where small changes could build on one another instead of being wiped away, where stability wasn't imposed from the start, but earned through a precise sequence of early events. And when we step back and compare this long, quiet history to what we see elsewhere in the galaxy, another question begins to emerge. If stability like this is so important, and if it's so hard to achieve, then how many systems like ours could we realistically expect to find? And more importantly, have we been searching for them in the right way at all? But for decades, we may have been looking for this kind of stability in all the wrong places. By this point in the story, a tension has been quietly building. On one hand, the solar system appears rare, ordered, stable, and missing the most common kinds of planets we see elsewhere. On the other, the universe is vast, filled with stars and worlds beyond counting. It feels unlikely that a structure like ours would exist only once. So where does that leave us? The answer may not lie in the universe at all. It may lie in how we've been looking at it. For most of the exoplanet era, our understanding of planetary systems has been shaped by two main observational methods. Both are powerful. Both have transformed astronomy. And both come with built-in limitations that quietly steer what we see. The first is the transit method. This technique watches for tiny dips in a star's brightness when a planet passes in front of it. Each transit blocks a small fraction of the star's light, creating a regular, repeating signal. The method is elegant, precise, and incredibly effective when the conditions are right. But those conditions are very specific. For a transit to be visible, a planet's orbit has to be aligned just right with our line of sight. More importantly, the planet has to pass in front of its star often enough for astronomers to be confident it's real. That means short orbits, planets that circle close to their star transit frequently. Days, weeks, sometimes even hours. Their signals repeat again and again, building confidence quickly. Planets farther out take longer, much longer. A Jupiter-like planet orbiting once every 10 or 12 years might transit only once, or not at all, during the lifetime of a mission. So transit surveys naturally favor compact systems filled with close-in planets. Not because those systems are necessarily more common, but because they are easier to detect. The second major technique is radial velocity, sometimes called the Doppler method. Instead of watching for dimming light, This method measures a star's subtle back-and-forth motion caused by the gravitational pull of its planets. As a planet orbits, it tugs on its star, causing tiny shifts in the star's spectrum. This approach excels at finding massive planets. The heavier the planet, the stronger the tug. But here again, distance matters. A large planet close to its star produces a strong, rapid signal. A large planet far away produces a slow, gentle one. To confirm that slow signal with confidence, astronomers must observe the system for many years, often decades. And that's where the blind spot opens. A Jupiter analog, massive, distant, slow-moving, is one of the hardest kinds of planets to confirm with either method. Its transits are rare or non-existent. Its gravitational signature unfolds gradually, requiring patience and long-term monitoring that few surveys were designed for. Now consider what that means. The planets that may matter most for long-term stability, the distant giants that shape entire systems, are precisely the ones our earliest tools were least likely to find. This doesn't mean astronomers were careless. It means they were efficient. They built instruments to detect what was detectable. And in doing so, they constructed a picture of the universe based on the loudest signals: fast orbits, close-in planets, crowded systems. Those features dominated the data not necessarily because they dominate the galaxy, but because they dominate our measurements. Over time, this created an illusion. It began to feel as though compact systems were the rule, and calm, spread-out systems were the exception. The absence of solar system-like architectures started to look meaningful, even alarming. But absence of evidence is not evidence of absence. A quiet system doesn't announce itself. A stable orbit doesn't flash repeatedly across a detector. A distant giant planet takes years to reveal its influence. If you only listen for loud signals, you'll miss the quiet ones. Not because they aren't there, but because they require a different kind of attention. This realization resolves a major contradiction. The solar system looks rare not necessarily because it is rare, but because it is subtle. Its defining features are slow. Its architecture unfolds over long time scales. Its most influential planets move patiently, shaping the system without drawing attention to themselves. In other words, we may have been searching for the solar system in all the wrong places. For decades, our surveys were optimized for speed and repetition. They excelled at finding what moves quickly. But the solar system is a system defined by restraint, by distance, by long-term balance rather than immediate motion. That doesn't mean we were wrong. It means we were limited. And science progresses by recognizing its limits. Once astronomers began to understand this bias, a new question emerged. If our methods were tuned to motion, what would happen if we focused instead on something slower, something steadier? What if, instead of measuring how stars wobble, we measured where they are, how they shift against the distant background over time? That shift would be tiny, almost imperceptible. But over many years, it could reveal the presence of distant, massive planets without relying on repeated transits or rapid motion. It would require extraordinary precision and extraordinary patience. But it would open a new window, a way to find the quiet systems, the wide systems, the ones that don't shout. And that realization led astronomers toward a different approach, one that didn't track motion through speed, but through position. To find what we've been missing, we had to stop measuring motion and start measuring position. For decades, our picture of planetary systems was built by watching stars move back and forth. measuring speed, rhythm, and repetition. It worked well, but it left a quiet gap. The slowest, widest systems remain difficult to see. Astrometry takes a different approach. Instead of measuring how fast a star moves, astrometry measures where it is, its exact position in space, tracked carefully over time. Not once, not twice, but again and again, with extraordinary precision. Imagine watching a distant street light from miles away. You wouldn't notice it shifting side to side, but if you could measure its position down to a fraction of a hair's width, you might detect a tiny, rhythmic sway. That sway wouldn't come from the light itself, but from something unseen pulling on it. That's what astrometry looks for. When a planet orbits a star, both objects move around a shared center of mass. The star doesn't stay perfectly still. It traces a small, slow loop in space. For close-in planets, that loop is tight and fast. For distant, massive planets, the motion is broader, but far slower. This is where astrometry shines. A Jupiter-like planet produces a subtle but wide wobble. The movement takes years to complete, but the shift in position is larger than that caused by small, close-in worlds. You don't need repeated transits. You don't need perfect known alignments. You only need patience and precision. That's where Gaia enters the story. Launched in 2013, Gaia was designed to do something unprecedented. Measure the positions of more than 1 billion stars with accuracy never before achieved. It doesn't stare at one system for a short time. It scans the entire sky repeatedly, building a long-term record of stellar positions. Over months, then years, Gaia watches stars drift ever so slightly against the distant background. Most of that motion comes from the star's own paths through the galaxy. But layered on top of that are tiny deviations, minute shifts that hint at something else, something orbiting. The level of precision involved is difficult to grasp. Gaia can detect changes in position smaller than the width of a human hair seen from thousands of kilometers away. It's sensitive to motion so small that earlier instruments would have dismissed them as noise. And unlike transit surveys, Gaia doesn't care whether a planetary system is neatly aligned with our line of sight. It doesn't need planets to pass in front of their star. It simply measures where the star is, and whether that position changes in a way that can't be explained by motion alone. This makes Gaia uniquely suited for one specific task: finding distant giants. The very planets that were hardest to detect before, massive worlds orbiting far from their stars, are exactly the ones Gaia is built to reveal. Their influence is slow, steady, and spread out over time. Perfect for a mission that values consistency over speed. In a sense, Gaia was designed for systems like ours. It watches patiently. It measures quietly. It waits long enough for subtle patterns to emerge. For the first time, astronomers had a tool that didn't favor crowded, compact systems by default. A tool capable of uncovering wide architectures and long-period planets, systems shaped by distance and restraint rather than urgency. And once Gaia had gathered enough data, the picture began to change. Not dramatically, not all at once, but just enough to suggest that something had been hiding in plain sight. Almost immediately, Gaia began to reveal things we'd never seen before. It didn't take long for Gaia to prove that this new way of seeing truly worked. As the mission's early data sets were analyzed, astronomers began to notice stars whose positions didn't quite behave as expected. Their motion through space was smooth, but layered on top of that smooth motion was a slow, repeating deviation, too regular to be noise, too large to be coincidence. These were the signatures Gaia had been built to find. Among the first confirmed discoveries were massive planets now known as Gaia 4b and Gaia 5b. They weren't small worlds tucked close to their stars. They were gas giants, heavy, distant, and patient, moving along wide orbits that took many years to complete. In other words, they were exactly the kind of planets that earlier methods struggled to detect. Their stars didn't dim regularly. Their gravitational pull didn't produce sharp, rapid signals. For transit surveys and traditional Doppler measurements, these planets were almost invisible. But in Gaia's positional data, their influence was unmistakable. Each planet revealed itself not through speed, but through persistence. The stars hosting these worlds traced slow, gentle loops across the sky. The motion unfolded over years, not days. And because Gaia measured position directly, again and again, those loops could be reconstructed with growing confidence. Of course, discovery alone isn't enough in science. To confirm these planets, astronomers combined Gaia's measurements with other observations. Radial velocity data helped constrain mass. Direct imaging ruled out alternative explanations. Together, these independent lines of evidence converged on the same conclusion. Massive, long-period planets were there, shaping their systems quietly from afar. The importance of these discoveries wasn't in their number. At first, there were only a handful. But that handful mattered enormously because they demonstrated something crucial. Gaia could do what no previous mission had done reliably. It could detect Jupiter-like planets without needing perfect alignments or short orbital periods. It could uncover the kinds of giants that define a system's architecture rather than dominate its inner regions. In a sense, these early finds reopened a door that had been nearly closed. For years, the absence of distant giants in exoplanet catalogs had influenced how astronomers thought about planetary systems. Compact architectures felt dominant. Wide, orderly systems felt exceptional. Now, that narrative had to be reconsidered. These planets hadn't suddenly formed. They hadn't appeared out of nowhere. They had always been there. We simply hadn't had the right tool to see them. That realization brought a quiet shift in perspective. If even a limited amount of Gaia data could reveal planets like these, then the universe might be holding far more familiar architectures than we once believed. Systems shaped by distant giants, long-term stability, and slow, deliberate motion. What mattered most wasn't the specific planets Gaia found first. It was the proof of concept. Gaia had shown that the missing pieces could in fact be found. That wide orbits and long periods were no longer barriers. That the calm systems, the ones that don't shout, were finally within reach. And if just a few years of data could reveal this much, the implications for the future were profound. Because Gaia was still watching. For years, the search for exoplanets felt like a series of remarkable but isolated discoveries. One planet here, another system there. Each finding added to our knowledge. But the bigger picture remained blurry. Gaia Data Release 4 marked a turning point. For the first time, astronomers weren't just collecting snapshots. They were working with a continuous record, about 5.5 years of precise positional measurements for stars across the sky. This long time span changed what was possible. Astrometry depends on patience. A distant giant planet doesn't reveal itself quickly. Its influence unfolds slowly, tracing a gentle curve that only becomes clear after years of careful observation. With shorter data sets, those curves remain incomplete, suggestive but uncertain. DR4 changed that. With enough time, the slow wobble caused by long-period planets could finally be separated from a star's own motion through the galaxy. Signals that once blended into the background began to stand out as coherent patterns. This mattered most for one reason. Planets like Jupiter take a long time to orbit. 10 years, 12 years, sometimes more. Detecting them requires watching patiently through a large fraction of that journey. DR4 provided the first data set long enough to do this reliably across a vast number of stars. As a result, astronomers expected a dramatic shift, not just in how many planets would be found, but in what kinds. Scientific forecasts suggested that Gaia's full astrometric data could reveal thousands of new exoplanets. Estimates ranged from roughly 6,000 to 8,000, with the majority being massive gas giants on wide, slow orbits. These are not the flashy planets that transit surveys excel at finding. They don't circle their stars every few days. They don't produce sharp, repeating dips in brightness. Instead, they shape their systems quietly, from afar. And that's exactly why they matter. Because giant planets on wide orbits are architects. They influence the spacing of inner worlds. They control the flow of debris. They determine whether a system settles into long-term calm or remains dynamically restless. With DR4, astronomers weren't just counting planets anymore. They were beginning to see structure. Patterns started to emerge across many systems at once. Which stars tended to host distant giants? How often those giants appeared alone, and how often they shared space with inner planets. Whether wide-orbit giants were associated with calmer inner architectures or with signs of past disruption. This was a shift from discovery to diagnosis. Instead of asking, "Is there a planet here?" scientists could now ask, "What kind of system is this?" That distinction is subtle, but profound. A single planet tells you very little. A system tells you a story. Gaia DR4 was the first step toward reading those stories at scale. Not one system at a time, but thousands. Each with its own history, its own balance of order and chaos. And for the first time, it became possible to test ideas that had once lived mostly in simulations. Ideas about migration, about stability, about whether systems like ours were genuinely rare or simply overlooked. This wasn't just another catalog update. It was the beginning of a census. A careful accounting of planetary systems as complete structures shaped over billions of years. A way to compare architectures, not just individual worlds. But even with DR4, the picture was still incomplete. Some of the slowest giants hadn't finished revealing their paths. Some of the widest systems still required more time to separate signal from motion. To truly understand how rare our solar system might be, we needed to keep watching. If Gaia DR4 marked the beginning of a true census, then Gaia Data Release 5 represents its full maturity. By the time DR5 is complete, Gaia will have observed the sky for more than 10.5 years. In astronomy, that length of time changes everything. It's long enough to follow a full orbit of a Jupiter-like planet. Long enough to trace the slow dance of Saturn-sized worlds. Long enough to separate short-term motion from long-term structure. For the first time, we won't be inferring planetary systems from fragments. We'll be seeing them whole. With this extended timeline, scientific estimates grow dramatically. Instead of thousands, Gaia is expected to reveal on the order of 100,000 exoplanets, or possibly even more. And crucially, these won't be dominated by the close-in worlds that shaped early catalogs. They will include vast numbers of distant giants, moving slowly along wide, stable paths. This is where the long view becomes transformative. Time allows Gaia to observe complete orbital arcs. It allows astronomers to distinguish between temporary fluctuations and true gravitational signatures. A planet that once appeared as a hint becomes a confirmed presence. A partial curve becomes a closed loop. And when those distant giants are finally mapped, something new becomes possible. Their data can be combined with what we already know. Kepler and TESS have shown us the inner regions of planetary systems, small worlds, short orbits, compact arrangements. Gaia reveals the outer regions, the massive architects that shape everything inside. Together, these data sets offer something astronomy has never had before. A full structural view of planetary systems, inner planets and outer giants, fast orbits and slow ones, crowded regions and quiet space. For the first time, we can ask a question that once seemed out of reach. How many systems truly resemble ours? Not just in the presence of a planet like Earth, but in overall layout, in spacing, in long-term stability. With DR5, the debate shifts decisively. The question is no longer whether solar system-like architectures exist elsewhere. It's how often they appear and under what conditions. Time, it turns out, was the missing instrument. Not better sensors alone, not clever algorithms, but the patience to watch slow systems unfold on their own schedule. And this leads us to a moment of genuine anticipation. Gaia's data may reveal that systems like ours are more common than we once believed. Quietly present, overlooked because they don't announce themselves. Or it may confirm the opposite. That threading together a stable star, migrating giants, missing super-Earths, and billions of years of calm is extraordinarily difficult. Either answer would be profound. If systems like ours are common, then the galaxy may be filled with long-lived, orderly environments where complexity has time to grow. If they are rare, then the solar system represents a fragile outcome, a narrow path taken once among countless alternatives. Gaia will not choose the answer for us, but it will finally give us the data to see which story the universe has been telling all along. And whichever answer Gaia gives us, it will change how we see our place in the universe. So we return to the question that guided this entire journey. Is our solar system rare? After everything we've seen, the migrations of giant planets, the missing worlds, the narrow windows of timing, the quiet stability that followed, we still don't have a final verdict. And for now, science is comfortable with that. There are two possible answers. If systems like ours turn out to be common, then the universe may be filled with calm, long-lived places where complexity has time to grow. Worlds that don't announce themselves loudly, but persist quietly for billions of years. In that case, life may not be unusual. It may simply require patience to find. And if systems like ours are rare, then the stability we experience becomes something else entirely. Not a guarantee, not a default, but a fragile outcome, one shaped by chance, timing, and restraint. A reminder that long-term calm is not easily achieved in a universe built for motion. Either way, the science continues. Gaia will keep watching. Data will keep accumulating. Answers will slowly take shape. But tonight, those answers don't need to be settled. Because regardless of what the final numbers reveal, the reality around you remains the same. Right now, the planets follow their familiar paths. Their orbits are nearly circular, steady, and predictable. Jupiter and Saturn move slowly in the distance, far from the inner worlds. The asteroid belt stays where it has been for billions of years. The Kuiper belt drifts quietly at the edge of the sun's reach. The The sun itself shines with calm consistency. No sudden flares, no violent changes, just a steady flow of energy, arriving on Earth after an 8-minute journey through space. There is no catastrophe unfolding, no planetary upheaval underway, no cosmic emergency demanding your attention. The universe, at this moment, is doing what it does best when conditions are right. It's staying quiet. That quiet is easy to overlook. It doesn't feel dramatic. It doesn't feel heroic, but it's the foundation beneath everything else. The reason oceans can remain liquid. The reason climates can persist. The reason life doesn't have to start over every few million years. Life doesn't need the universe to be kind. It doesn't need perfection. It just needs stability. And for billions of years, this small system has provided exactly that. Not because it was designed to, not because it was destined to, but because a long chain of events, some violent, some gentle, eventually settled into balance. You're living inside that balance now. As you rest, the Earth continues its quiet spin. The moon keeps its steady watch, holding the planet's tilt in place. The sun moves slowly through the galaxy, carrying this system with it, unchanged on human timescales. Whatever Gaia ultimately tells us, whether systems like this are rare or quietly abundant, doesn't change the present moment. Tonight, you are safe. Tonight, nothing needs to happen. The universe is vast, and most of it is beyond our control. But here, in this small corner, the conditions are calm enough to allow rest. So you can let the questions drift for now. Let the data wait. Let the answers arrive in their own time. Tonight, the universe is quiet enough for you to rest.